So for this function, Laplace transform t power a will be equal to s power a plus 1, and in the integral you will get e power minus x and into x power a, e power minus x into x power a dx, and then from 0 to infinity. Here actually we will use a transform which is equal to s times t is equal to x. Okay, so t is equal to x over s and dt will be equal to dx over s. So this integral is a special function which is called as the gamma function. So it will be s over a plus 1 into gamma a plus 1. Okay, so so this is the gamma function. So although we will derive this, we have derived this gamma 1 plus 1 function, but it is not very much used in the calculations, but still we can derive it. And then of course this gamma plus 1 function, gamma a plus 1 function, which is for t power a, is useful for the deriving of the other formulae as well. Okay, so now let's talk about a theorem which is called as the S shifting theorem. So S shifting theorem. So what does it mean by the S shifting theorem? So for example, if we know that the transform of a function f of t is equal to 0 to infinity e power minus st, f of t is here, is this. So then what is the transform of a function f of s minus a? Okay, f of s minus a. So by the definition we can write that its transform will be like this, because we are replacing s by s minus a. So here we will also replace s by s minus a as well, and then f of t dt. So we can write it like this also, 0 to infinity e power minus st into e power at f of t dt. So if we take this e power at f of t as one function, and then that function is being multiplied by e power minus st, so we can say that f of s minus a. So this, we can say that this is a Laplace transform of, this expression is a Laplace transform of e power at times f of t. So this gives rise to the theorem which is called as the S shifting theorem. So which means that if we have a function and if you multiply this function by e power at or e power minus at, a power at, okay, then its Laplace transform will be the Laplace transform of this function ft, where t will be replaced by s minus a, where s will be replaced by s minus a. Okay, so what does it mean? It means that, for example, if I have this function like f of t is equal to 1, and I know that its Laplace transform is 1 over s, the very first formula which we derived. So then in that case, what will be the Laplace transform of a function s minus 1? Okay, so what will be the Laplace transform of f of t times e power at times 1? Okay, so it will be f of s minus a, that will be 1 over s minus a. Okay, that will be 1 over s minus a. Yeah, so I think we have derived this formula before as well, right? The second one. So similarly we can apply this technique. So this technique now we can apply for deriving the function like this. So for example, if we want to find the Laplace transform of e power at cosine of omega t. Okay, so we already know that the Laplace transform of cosine of omega t was we already have found out cosine of omega t. The Laplace transform was s over s square plus omega square. Okay, we just found out before. Let me see here where it was here. Okay, s over s square plus omega square. So then that means, so then what will be the Laplace transform of e power s minus at? So it will be then, because we are multiplying it by e power at, so s will be replaced by s minus a. So it will be s minus a over s minus a square plus omega square. Okay, so that will be the Laplace transform of e power at into cosine of omega t. And this of course can be proved by the definition of the Laplace transform. So this type of thing we can this type of analogy we can use for finding the inverse transform, and later on, of course, inverse transform we will find out quite a lot later on, but let's see one example. So for example, find the inverse Laplace transform of if f of s is equal to 3s minus 137 over s square plus 2s plus 401. So it is a cleverly written Laplace transform. We need to find its inverse Laplace transform. Inverse means, for example, when we do the Laplace transform, so what does the Laplace transform do? Laplace transform transfers a function of t into a function of s. So when we take the inverse of that, then what we will do is we will go from a function of s to function of t. So we have to find the function of t. Okay, so that will be the Laplace inverse of this function. Okay, 3s minus 137 over s square plus 2s plus 401. So Laplace inverse of this we can easily find. So if we can see that this s square plus 2s plus 1 we can write like this: s plus 1 square. Okay, so it will be s square plus 2s plus 1, and then we take 1 from 400, so it will be 400. So 400 is 20 square. Okay, and then on the top over here we have 3s, so 3s, and then I can add 3 from here, so that I can take 3 common, and then it will be s plus 1, so that we can just somehow find this format over here: s minus a over s minus a square over omega square. So in this way, then I have wrote it 3s plus 1, so it was minus 137. So for minus 137 it should be minus 140, right? So then these two are equivalent. So now Laplace inverse of this. So then now I can write it like this: 3 into s plus 1 over s plus 1 square plus 20 square, and then I can write it like this: minus 7 into 20 over s plus 1 square plus 20 square. So by analogy now I know that this is the Laplace transform of cosine function, and this is the Laplace transform of sine function with their respective s shifting. So now I can write it like this 3, and then this is for cosine. Okay, but with s shifting it should be e power minus 1t. Okay, e power minus t times cosine omega t. Omega is in this case 20 t, and minus, and this is for the sine, because for the sine omega is here, for the cosine s is here, so it will be minus 7 e power minus t. Is for this is also the shifting of s, and then sine of 20 t. So in this way we can find the inverse Laplace transform of this function. Okay, so with this, with the derivation of the formula, so we have now found out the Laplace transform of 1 t square t power n plus 1. We have also found the Laplace transform of t power a. We have found the Laplace transform of e power at. We have found the Laplace transform of cos, hyperbolic, sine, hyperbolic. We have found the Laplace transform of cosine, cosine function, sine function. Okay, and then we have also found the Laplace transform of e power a t times cosine, or e power at times sine function. So these are some of the basic Laplace transforms which are used quite often, okay, in the solution of the differential equations. Of course, there is a bigger list as well, which you can see in the book, and then there are some additional derivations which will be needed for the differentiation, how to replace the derivative of a transform into a Laplace function. So that we will see in the next section. And then after that we will be able to use the Laplace transforms for the solution of the differential equations. Okay, that's all for this video clip, and then I will continue with the next topic in the next video clip.